Welcome back. We cover in this segment a motion estimation technique, phase correlation, which is suitable for estimating the global motion an image frame is undergoing. It is therefore also referred to as an image registration approach. The algorithm is rather intuitively clear, and it is based on a simple property of the Fourier transform that we covered in week 3. So we see that we make use of the important information we covered last week right away. We describe the property in terms of the continuous Fourier transform first, but we also discuss the actual implementation of the algorithm in terms of the discrete Fourier transform, which is the computable transform as we know by now. So let us proceed with this segment. We will describe next some of the most commonly encountered methods for estimating motion estimation methods. They're grouped into direct methods and indirect ones. With direct methods, we compute the optical flow in the scene. They come under different names. Phase correlation, we try to find the shift between two frames by estimating the phase component that results due to the shift in the frequency domain. Block matching methods, as the name implies, we take one block in one frame and try to match it to the most appropriate location in another frame. Then there are the methods that compute the spatial and temporal gradients in the scene, and they come in under two names. The traditional name here is optical flow algorithm. It gives us the optical flow equation, which I can use to find the motion, and then Pell recursive methods, which also estimate the optical flow, but in such a way so as to allow recursive computability of the vector field. Within direct methods, I first find the features in the two frames and I match the features directly, which of course will result in an estimation of the motion. Let us explain the phase correlation method with the use of an example. Consider the image shown here. Noise has been added to this image, and also a translated version of this image as shown here. It should be clear that if I translate the first image in approximately the diagonal direction, I should obtain the second one. Let us denote by x, n1, and 2 the first image, and the second one by x, n1 minus m1, and 2 minus m2, the two translations in the horizontal and vertical direction. Based on what we have learned about the Fourier transform, if x, omega 1, omega 2 is the Fourier transform of the first image, then the Fourier transform of the second one equals e to the minus j omega 1 m1, e to the minus j omega 2 m2 x omega 1 omega 2. So the magnitude of the Fourier transforms of the two images is the same. However, I have this linear phase component due to the shifts in the spatial domain. My objective clearly is to estimate M1 and M2. If I manage to isolate this phase component, these complex exponentials, and take them back to the spatial domain, then I know that they will give rise to a delta at M1, M2. So if I do everything right, I'll obtain an image as shown here. So there is indeed a delta here. It's approximately at 30, 33. So these are the shifts, M1 30, M2 33. So if I shift the second image by minus 30, minus 33, I should obtain the first image. So let us now look at the algorithmic details that will allow us to obtain this phase correlation image that will give us an estimate of the shifts. Let us now look at the algorithmic details behind the phase correlation method, which is also categorized as a registration method. We are given two frames from a video sequence at times t-1 and time t, and the first step is to take the discrete Fourier transform of these frames shown here correspondingly as xt-1 and x of t, k1, k2. Now, in the previous example, I used the continuous Fourier transform to describe the method, But we know by now that the continuous Fourier transform is not a computable transform, so therefore when I need to take an image to the frequency domain, I use the discrete Fourier transform, or of course through one of its fast implementations, so I use an FFT. The modeling assumption is that the one frame is shifted with respect to the other frame. So the frame at times t equals the frame at times t minus 1 shifted by m1 in the one direction and by m2 in the other direction. These shifts, however, are not linear shifts, but circular shifts, or modulo n1, modulo n2 shifts. If you recall, one way to explain circular shifts is to take an n1 by n2 image, periodically extended by n1 in the one direction and period n2 in the other direction, and then perform a linear shift, but only extract the base period, the period in one direction between 0 and n1 minus 1, and the period between 0 and n2 minus 1 in the other direction. Now, in most cases, the images are not related by a circular shift, like the example we showed, but by a linear shift. So to account for that, we first window, with a two-dimensional window, both images before computing their DFTs. There are a number of different windows one can use from digital signal processing, like the triangular window, Kaiser window, and so on. So the reason for this windowing is to downweight the contribution of the pixels around the boundaries of the image, since, again, the images are not related necessarily by circular shifts. Then, based on the shifting property of the discrete Fourier transform, we know that the two images are related in the frequency domain as shown here. So the DFT of x of t equals the DFT of x of t minus 1, and the shifts, the circular shifts in the spatial domain, give rise to this phase component here, right? These linear phase components that multiply the spectrum. So again, the two images have the same magnitude of their DFTs, but in their phase of the second one, I have added this linear phase component. So having computed the DFTs of the two frames, the next step is to compute this correlation image, C of K1, K2. So it's the DFT of x of t times the x of t minus 1, and this is the complex conjugate of the complex number, so it leaves the magnitude unchanged and changes the sign of the phase, and in the denominator I take the magnitude of these two terms. So if I substitute from the equation above x of t in here, then we'll see that I have x of t minus 1 times x of t minus 1 complex conjugate, which will give me the magnitude of the DFT times the phase component. So in other words, I'm going to get this expression, and we see here that the magnitudes cancel out, and all I'm left with is these complex exponentials, this phase component. The third step I have to take is to take now this image back to the spatial domain, and we do know that the inverse discrete Fourier transform of these complex exponentials is just a delta. So this image here is 0 everywhere except at the pixel with coordinates m1, m2, where the value is equal to 1 due to the existence of this delta. So performing these three steps I just described, we'll be able to see where this delta is located in this image Cn1 and 2, and obtain an estimate for the shifts m1, m2, which will allow me to register the t minus 1 frame back to frame t.